Hi students, in this video we're going to be covering section 8.9, which is all about bond properties. So we're going to delve a little bit farther into some details about our, single bonds, double bonds, triple bonds, etc., the energy involved, a little bit of crossover with some thermo stuff from before. So let's just jump right in. So first, one bond property we can discuss is bond order. Okay, so what is bond order? It's essentially a number that's going to tell you the ratio of the shared pairs of electrons between two atoms and how many linkages or link locations there are in the molecule. So it's essentially going to be a number that's going to kind of give us some information about the strength of that bond, because the higher that bond order number, the stronger the bond will be. Now, a lot of the times these are whole numbers. So if we're talking about a single bond, our bond order would be 1. If it's a double bond, our bond order would be 2, etc. So those are pretty normal, but where it's really going to come into play is when we talk about our resonance structures. But if I look at a simple molecule, we could pick either one of these. Let's just look at CO2. If I sketched out my Lewis structure for CO2, we've done this many times at this point, it looks like this. Okay. Now, if I wanted to calculate the bond order, we need to just think a little bit about how the question's being phrased. The question may say, what's the bond order between C and O in one particular place in the molecule? In which case it would be 2 here because we have a double bond. It may also ask about what's sort of the overall bond order of C to O throughout the entire structure. So just make sure you're paying attention to the wording of the question. We'll see this pop up in our next example. But if I look at this CO2 example, if I calculate it, I calculate my bond order like you see here. So the number of shared pairs linking X and Y. Well, again, looking at the C to O combinations here, there are 1, 2, 3, 4 shared pairs involved in the bond there. And we're dividing that by how many XY links, in this case, how many CO links there are in the structure. Not necessarily single versus double, but just how many times are C and O connected. Here's one, and here's the other. So if I divide then, I would see my bond order throughout this molecule is 2. And that tracks because I have a double bond here and a double bond here. So that's not surprising that our overall bond order in this molecule is 2. Okay. If I look at CH4, just doing that quickly, CH4 would be a tetrahedral, but the Lewis structure would look like that. So we would see that our bond orders throughout that CH4 would all be 1 because they're all single bonds. Okay, but where bond order really, again, is relevant is when we're talking about resonance. Okay, so when we're looking at a resonance or a molecule that displays resonance, our bond orders are going to be fractions because remember, we have electrons that are kind of spread out in a couple different locations. So we draw these resonance structures to try and show the different possible places those electrons are spread out throughout, but remember, in reality, they are in fact spread out evenly across all. So if I look at this ozone example, I'll just sketch this out quickly here for you to save some time. But if we look at our Lewis structure for ozone, it looks like this. So that would be one resonance structure. Alternatively, this would be our other one. Whoops, that's the same one. That would be our other Lewis structure there. Okay, so here are 2 resonance structures for ozone. Now, if I go to calculate my bond order using that formula we had on the previous slide, we said it's if I look at this one on the left to start, the number of shared pairs linking X and Y, in this case, linking O and O. So I see that there's 1, 2, 3, so 3 pairs, 3 shared pairs, and there are 1, 2 O to O connections. So what I see is my bond order is 1.5 essentially. Okay, so that means in reality for both, and whether I calculate it for this one on the left or this one on the right, I would get 1.5. So the bond order throughout this entire molecule is 1.5. So in reality, rather than it being a single and a double, you'll sometimes see these structures, we haven't really seen them this year this way, but you'll sometimes see these structures drawn more like this instead, where I'm showing, I'm actually just going to leave off the electrons on the outside. But if we're just looking at the center, or the central atom there, we can see that in reality, rather than it being a double and a single, that extra bond is kind of, the electron density is spread out evenly between these 2 locations. So it's kind of like a 1 1/2 and a 1 1/2 bond there. We still have this lone pair of electrons in the center, but regardless of our resonance structure, our bond order throughout this molecule will be 1.5. Okay. Now, the next bond property we're going to discuss is bond length. So let's tie this in with our knowledge of strength as well. So the bond length is the distance between the nuclei of a covalent bond. So in other words, if you look at this picture at the bottom, if I had a carbon-carbon bond, again, we know these have these electron clouds, but if I kind of estimate our atom here, our nucleus would be at the center, and then I would say, okay, the distance from the center of one to the other, that's going to be our bond length. That's the distance from one nucleus to the other. Now, what we know is that the stronger the bond, the shorter the length will be. Now, how do I know if the bond is stronger or not? Again, it's going to tie into that bond order. So if I calculate that, we know, again, it's typically either a whole number, if it's just a regular double, single, triple bond, or it could be fractional. But the bigger that bond order number, the stronger the bond, and therefore the shorter the length. Envision kind of the extra bonds pulling those atoms closer together. We also see that the more polar the bond, the shorter the length as well, because if I have a more polar bond, that means I have a bigger electronegativity difference between the two atoms involved in the bond, so kind of a bigger positive-negative charge differential, which will also make those atoms pull closer together as well. So just as a comparison, if I have this carbon-carbon single bond, which should have a bond order of 1, this carbon-carbon double bond, which should have a bond order of 2, or this carbon-carbon triple bond, which should have a bond order of 3, you can see that my bond is getting shorter as that bond order increases. Now this A with the circle on top, that is it's another length unit, it's angstroms. So that's sort of an English unit, not really in the metric system, but you'll see that pop up from time to time when we're talking about really short lengths. Okay, so that's our bond length. Now, you can find these numbers in your reference booklet should you need them. They are on page 8 in your reference booklet. I believe they are in picometers, not angstroms, but it still gives you the relevant info you need. So if you need to actually look up the length for some reason, you can do that in the reference book. Now, what we're going to spend the rest of this section talking about, this is where it starts to cross over a little bit with our thermo unit previously. We're going to talk about bond association energy. Sometimes you also hear, bond association enthalpy, excuse me. So enthalpy, remember we talked about that previously. So when we were talking about our bond association, or when we were talking about enthalpy previously in our thermo chapter, we knew that was our delta H. So we'll see a similar type of calculation as we work our way through here. But what is our bond dissociation energy? It is the energy needed to break a covalent bond, specifically in the gas phase. But we're just kind of thinking about, just like how we talked about ionic compounds dissociating back earlier in the year, we're talking about a covalent molecule here dissociating as well. Okay. Now, what we can see is that if we're thinking about how much energy is involved in that dissociation process, the higher the bond order, i.e. the stronger the bond, the more energy it will take to separate those two atoms. And again, that makes sense, right? If it's a stronger bond, they're more strongly attracted to one another. We would need to put in more energy to break that attraction. Okay. Now, just like with our bond lengths, we can actually look these values up, and we can look up these values and use them in an equation similar to one we've seen before. So if we wanted to estimate the enthalpy of a reaction, so not just of the energy involved in one molecule, but if we're looking at a chemical reaction and we wanted to estimate the enthalpy involved when that reaction occurs, we can use this new version of our summation equation. So previously when we saw our summation equation in chapter 5 in our thermo chapter, we talked about delta HF minus delta HI. So the sum of the delta H's of our products minus the sum of the delta H's of our reactants. When we're talking about this in terms of Lewis structures and covalent molecules and things like that, if we're going to calculate it using bond dissociation enthalpies, then we would have to change it slightly to this. So our delta H for the reaction would be the sum of the enthalpies of all the bonds broken minus the sum of all of the bonds formed. Okay, now keep in mind the bonds broken are actually going to be the ones on the reactant side, and then the bonds formed are going to be the ones on the product side of the reaction. Okay, so we'll kind of have to take an account of all the ones being broken, all the ones being formed. The easiest way to do this is by drawing the Lewis structures and then going from there. Now, before we get into our examples, just some things to note. Keep in mind that it does require energy to break a bond, right? Because you have to overcome that strong attractive force. Likewise, if you are forming a bond, the whole point of a bond forming is because it's, energetically preferable. So there will be energy released when that happens. Okay. Now, if I want to look up the actual values, you'll see a chart similar to this on page 8 in your reference booklet. So you'll notice that if I'm looking for example, the energy involved in a carbon to nitrogen bond, here's carbon, here's nitrogen, I'm just looking where they match up, and I would see that that would be 305 kilojoules per mole. So that's the energy in one carbon to nitrogen bond, essentially. So if I wanted to compare for any particular ones, I'm just looking where these elements match up in this chart. Now, keep in mind your chart will have both single bond values, that's going to be the larger one, and then there also is a separate chart for when you have multiple bonds, doubles or triples, things like that. So please just make sure you're looking at the appropriate table when you're trying to find these values. There are also ones in your textbook as well. I'll use the ones in the reference book, though, as we work our way through examples and things like that. But in a pinch, you can find these in the appendix of your textbook as well. So a standard question would look something like this. Calculate the delta H of the reaction for the synthesis reaction between gaseous, hydrogen, and chlorine. So let's first just start with what would that reaction look like. So I'm going to ask you to pause the video here and write out the balanced chemical equation for the process described here. All right, so here is our balanced chemical equation. It's a synthesis reaction. It says it's gaseous, so we're looking at all this being synthesized. Hydrogen and chlorine, both gas at room temperatures anyway. Now, when I go to calculate this, again, for our new version of our summation equation, we're looking at the sum of the bonds broken minus the sum of the enthalpies of our bonds formed. Okay, so the way to determine that, what's breaking, what's forming, is by looking at the Lewis structures. So if I sketch out the Lewis structures, I'll just do these quickly for you. These are relatively simple ones. But underneath the reaction, I'm going to draw what those are for each of these substances. Keeping in mind this one, we do have a 2 there because we have this 2 in front for HCl. Okay, so what I'm going to see is that my bonds broken, I'm going to have to break this hydrogen-hydrogen bond and the Cl-Cl bond. And then we're going to form 2 HCl single bonds. Okay, so if I look in my reference booklet and find the relevant values that go with these, I see that for our HH, if I look on page 8, that single hydrogen-hydrogen bond, that's going to be 436 kilojoules per mole. Chlorine-chlorine would be 243. And then the hydrogen-chlorine single bond would be 431, not accounting for the 2 yet. Okay, so when I go to do my work, my delta H would be the sum of the bonds broken, which is this 1 hydrogen-hydrogen bond, so 436, plus this 1 Cl-Cl bond, minus the sum of the bonds formed. Now my bonds formed this time, it's going to be this HCl bond, so this 431, but remember, there are 2 of them in the reaction, so 2 times 431. So when I calculate that, I'm going to get negative 183. Now my unit is just kilojoules. Why is my unit just kilojoules? Because remember, these values that came from the reference book were technically all kilojoules per mole, if you look in the header of the chart. And what we're doing, just like when we did this with our summation equation in thermo, is we're taking this value and we're multiplying it by the coefficient from our balanced equation, which remember is moles. So those moles are going to ultimately cancel out, leaving us with just kilojoules anyway. Okay, so this is an exothermic process. This would give off energy, meaning this would be, a reaction. We would expect to see this happen, barring any other sort of driving force overcoming there. Okay, so there's example 812. The next one is similar. I'm going to ask you to try this one. So looking here, it says calculate the enthalpy for the combustion of methane to produce gaseous CO2 and water. So first we'd start with our balanced equation. If this is a combustion reaction, you should be able to write that and balance it. Then go ahead and draw all your Lewis structures. And then if you feel up to it, you can try your calculation as well. But at a minimum, pause the video right now, and I want you to try and write the balanced equation and draw the Lewis structures underneath, and then press play. Okay, so your reaction would look like what you see here in blue, and then if I sketch out my Lewis structures, you can see those in pink here. I've also added the coefficients in front just as a reminder. Now, when you go to calculate, we're going to assume that everything breaks and then everything forms. Even if that's not necessarily the case, it makes it easier to keep track of rather than, trying to decide, okay, well, did this one stay or did this one fully change? So just assume everything on the left-hand side of the reaction breaks bond-wise and everything on the right-hand side makes or forms. Okay, so if I look up the C to H single bond value in my reference book, this would be 414 for here. Remember, there's going to be 4 of them though, because there are 4 single bonds in the structure. So my delta H for my bonds breaking, again, that's everything on this side. I would have 4 times 414, because there's 4 of those single carbon to hydrogen bonds. Now I would also have 2 of these OO double bonds forming as well. And that OO double bond, if you look in your reference book, says the value there is 498 kilojoules per mole. So I would do 2 times 498 because of that coefficient. So those are all my bonds breaking. On my product side, I'm assuming everything is forming. So a C to O double bond specifically in CO2 is 803 kilojoules per mole. And then our H to O single bond is 464. Okay, so I'm going to do 803. I am going to multiply that by 2 because there are 2 of them in this structure. And where you need to be careful is the end here. So we've got 2 OH single bonds, but remember we have that molecule twice. So it's really 2 times 2 times 464. In other words, 4 times 464. Okay, so if we do all of that, you'll see for your answer, I'm running out of room here, so I'll scooch it up here. That's going to give you negative 810 kilojoules. Okay, so there's my final answer for this question. But at this point, that is the end of section 8.9. As always, if you have questions, please just reach out to your teacher. Thanks.